See, when any gas or vapor, or we can say which one is at very low pressure. In gas tube, if it is excited, means suppose the electric discharge is passed through it, or we can say by passing the electric current through it. If it is excited, then it emit some radiations having different wavelength. So this particular radiations of different wavelengths emitted by the atom, that is called its atomic spectra. That is called its atomic spectra. Okay. And very first, this type of atomic spectra was obtained by scientist Bahmer for hydrogen atom in visible range. So he observed this thing in this particular atomic spectra. Which one was line spectra? Which one was line spectra? Are you clear about the continuous spectra and line spectra? Yes or no?
Yes, sir.
Yes, sir.
Good. Now this particular line spectra, that is called emission spectra. Suppose for the same one, if it is kept at lower temperature and if the white light is passed through it, then in the spectrum of white light, you will get the black lines exactly at the same positions of the emission spectra. So this type of spectra obtained, that is called absorption spectra. But here, one important thing that we can observe, that is discrete wavelengths are there. This is the line spectra. And here we can observe a specific pattern in this particular spectra. So as the wavelength decreases, the separation between the wavelengths also, or spectral lines, decreasing one. Okay. And Bahmer experimentally represented this thing for these particular spectral lines. All the wavelengths can be calculated with the help of one common equation. So a set of all the wavelengths or spectral lines whose wavelengths can be calculated with the help of a common equation, that is called spectral series. That is called spectral series. And this particular specific spectral series for hydrogen in visible range, which one was first obtained by Bahmer, and therefore this series that is called Bahmer series. And all the wavelengths of Bahmer series can be calculated with the help of equation 1 upon lambda equal to R into 1 upon 2 square minus 1 upon n square, where n that is 3, 4, 5, 6 and so on. Now here R, that is the Rydberg constant. Its value that is 1.097 into 10 raised to 7 meter inverse. Now here when you substitute n equal to 3, and when for n equal to 3 we calculate the wavelength, then that is called the wavelength of alpha line. Means first line that is called alpha line, second one is beta, third one is gamma, fourth one is delta, like that. And this is of hydrogen. Therefore, when here you substitute n equal to 3, then the wavelength obtained, that is called wavelength of H alpha line of Bahmer series. Then when you substitute here 4, then it is called the wavelength of H beta line of Bahmer series. Like that. So all these experimental observations were obtained. Clear up to this one? First thing. Okay. So after Bahmer, so many scientists worked in that particular direction to study the atomic spectra. So scientist Lyman obtained one series in ultraviolet region. Bahmer series was in visible region. So all the spectral lines of Lyman series can be calculated with the help of the common equation 1 upon lambda equal to r into 1 upon 1 square minus 1 upon n square, where n equal to 2, 3, 4 and so on. Now here if we substitute n equal to 2, then we will get very first line of the Lyman series. First line is always termed as alpha line. This is for hydrogen atom. So we can say when here we substitute n equal to 2, we get the wavelength of H alpha line of Lyman series. Then if we substitute n equal to 3, then we will get the wavelength of H beta line of Lyman series. Like that. Then after, different scientists obtained different spectral series. This next one, Bahmer, we already discussed. Parcen series. So for Parcen series, all the wavelengths obtained in that particular spectral series can be calculated with the help of common equation 1 upon lambda equal to r into 1 upon 3 square minus 1 upon n square, where n equal to 4, 5, 6, 7 and so on. And Parcen series was obtained in near infrared region. So in this equation, if we substitute n equal to 4, then we will get H alpha line of Parcen series. Like that, bracket series, that is in infrared region. For that, the common equation of the wavelengths of spectral lines 1 upon lambda equal to r 1 upon 4 square minus 1 upon n square, where n equal to 5, 6, 7. Then fund series. For that, the common equation for the wavelength of spectral lines 1 upon lambda, that is r into 1 upon 5 square minus 1 upon n square, where n equal to 6, 7, 8, and this one is obtained in far infrared region. So we can write the common equation for all the spectral series like 1 upon lambda equal to r into 1 upon m square minus 1 upon n square. We can calculate the frequency f equal to c by lambda. So equation of the frequency will be rc into 1 upon m square minus 1 upon n square. And here we have to put one condition, m is less than n. So if you take m equal to 1, then it should be less than n. So n that we have to consider 2, 3, 4, then we will get Lyman series. If you take m equal to 2, then n will be 3, 4, 5, you will get Bahmer series. Then after, if you take m equal to 3, then n will be greater than m always. So 4, 5, 6 onwards, we will get Parcen series. So in this way, we can prepare a common equation to calculate the wavelength of any spectral line of any spectral series. Clear to all of you? Now see, experimentally we obtain the line spectra. Okay, atomic spectra, that is the line spectra. Now if we think about Rutherford's atomic model, Rutherford suggested this thing: electron revolves around the nucleus. in different orbit depending on the energy possessed by it. Okay. Now, if electron is revolving, it implies that its motion, that is accelerated one. Centripetal acceleration will be there. And as per classical electrodynamics, if any charged particle is executing accelerated motion, then it emits the energy in the form of radiations. Okay, so now if electron is revolving, it emits the energy, then its energy will be continuously decreasing. It implies that it will move closer and closer to the nucleus. So its motion will be not circular one, but that will be spiral one. And after some time, the motion will be end up at the nucleus. એટલે છેલ્લે ન્યુક્લિયસમાં જઈને બેસી જશે. Okay? So, if this happens, then what about the stability of the atom? And if the motion of the electron is a spiral one, its energy is continuously decreasing one. There is no break in it. Then there should be the continuous atomic spectra. But here we are getting line spectra. It implies that now Rutherford atomic model was failed to explain these experimental observations. So we can say, no doubt, Rutherford's atomic model is partially successful. He suggested almost entire mass is concentrated at the center in the nucleus, and entire positive charge is also concentrated in the nucleus. Electrons are revolving around it. But why line spectra is obtained? Why not continuous one? Okay. And what about the stability of atom? So all these things were not able to explain. So at this stage, Rutherford's atomic model was failed. So scientist Bohr studied all these things, right? He studied Rutherford's atomic model, his experimental observations, as well as he studied all these atomic spectra, and then after he represented the atomic model, which one is known as Bohr model, which one is based on postulates. So Bohr's atomic model is based on postulates, and in that he combined classical electrodynamics and newly developed the concept of quantum mechanics. That concept of quanta of energy, photon, which we studied in chapter 11, dual nature of matter and radiation, right? In that we studied that particular concept. So Bohr combined these two and he represented the atomic model. But he represented this atomic model in the form of postulates. So now we have to discuss the Bohr atomic model and up to what extent it can explain the actual atomic structure that we have to discuss. Clear to all of you?